Alright, these guys are kind of fun. These are just derivatives, and we're going to use our power rule, combine it with the chain rule. So it's stuff that you've seen before, but don't forget, like if I have x to the n power, if y equals x to the n, then y prime equals x to the n minus 1 times n. And so what we're going to do is basically take the exact same steps with these guys. There's really no difference at all, but they're going to look weird for their answers. So over here, y prime. What's y prime equal to? Well, it's equal to the exponent, the square root of 2, times x to the square root of 2 minus 1 power. And that's it. That's all you can do. There's no other trickeration to that or anything crazy. That's it. We leave the exponent exact. Do not write a decimal exponent. Just leave it exact. Well, what about 2 plus sine 3x? Chain rule. So if u is equal to 2 plus sine 3x, then du dx is equal to cosine 3x times 3. And so now what we're looking at is y equals u to the pi power. Well, take the derivative of that. dy dx is equal to pi times u to the pi minus 1 times du dx. And what is du dx? 3 cosine 3x. So substitute back into your stuff for u and for du dx. And your answer then, dy dx is equal to 3 pi, okay, times cosine 3x times 2 plus sine 3x to the pi minus 1 power. And it looks really weird, it looks really strange, but you know what? This is an exact answer, and it's a good answer. You can't simplify it any more past that, so just let her roll. Alright, on this guy, what we're going to do is we're going to take the derivative of the natural log of x minus 3, and then we want to also state the domain of this. And so let u equal x minus 3, and so du dx is 1. Hey, that's easy. So f prime of x is equal to 1 over u times du dx, which is 1 over x minus 3. No problem, right? So now we want to find the domain, though. So the domain is a different animal here. Well, what number can't go down here in the denominator? 3. 3 cannot go into the denominator. All right. The other problem with this, though, that we have to pay attention to is anytime you look at a natural log, that number inside here has to be greater than 0. Okay, so this number inside here, whatever you get inside here, has to be bigger than 0. So not only can we not have x equal 3, but this also needs to be larger than 0. So what we would say, you can use interval notation is really easy for this guy. We would just say we would go from 3 to infinity. If you're not an interval notation person, the other thing that you could use, it would just be to say x has to be greater than 3. You can't be equal to, because that would give us a 0. And you can't be less than, because that would give us undefined in this part right here. But that's all there is to it. Okay, this is a toughie. We've got y equals x to the x power, and this is going to be a little bit of a challenging one to work with. We've got to be able to get the x out of the exponent. So when you have a variable raised to that same variable power, we have to solve this out just a little bit differently. And so what I'm going to do is I'm going to reach into my bag of tricks, and with y equals x to the x power, I'm just going to take the natural log of both sides. And this is a legitimate move because whatever I do to one side, I do to the other. And as long as I do the same thing on both sides, then I'm okay algebraically. And what does that give me? That gives me the natural log of y equals the natural log of x to the x. And this is okay. We don't have a problem with this. And in fact, this is really great because now I can take this x and get him out of the exponent. And so what I'm really going to be working with is the natural log of y equals x natural log of x. Now remember, the whole goal here is to find dy dx. That's our whole goal. So now we're ready, and let's take the derivative of both sides. So dy dx over here and d dx over here. And when we do that, the derivative of the natural log of y is going to be 1 over y, okay, times dy dx. Don't forget to implicit differentiation rules. Don't forget your implicit differentiation rules. And on the other side, you're going to have chain rule. You're going to have the chain rule right here for this guy. Here's your u. And you're going to have the chain rule right here for this guy right here. Here's your v. Okay? And so when you chain that guy out, the derivative of the first, which is 1, times the second, which is the natural log of x, plus the first times the derivative of the second, which is 1 over x. And so now what you're going to want to do is get that all cleaned up and get your dy dx all by itself. So how do you do that? Well, multiply both sides by y. And when you do that, you have dy dx equals the natural log of x plus 1 times y. And if you want to distribute the y, that's fine. And if you don't want to distribute the y, that's fine. But ultimately what you end up with, don't forget what y equals. Okay? Y equals this guy right here. So when you get done at the end, if you've got a y in your problem, and we do, then we're going to just replace that with x to the x. So my final answer, again, is going to look really interesting. But dy dx is equal to the natural log of x plus 1 times x to the x power. Okay, so we're going to check out how the flu spread at Memorial, and we've got an equation for this. P of t equals 100 over 1 plus e to the 3 minus t power. So we want to estimate the number of students infected, the initial number of students infected with the flu. And when we do that, basically what this means is we want to know what's going on that very first start day. So when this is at t equals 0, okay? When t equals 0, that's when we can figure out how many kids were initially caught with the flu. After, how fast was the flu spreading after 3 days? This guy is going to be dp dt, because that's going to be our rate of change, and then when t is equal to 3 days. And so that'll get us the next answer. And then to find when the flu is spreading at its maximum rate, we want to look for the maximum point on the graph, and we'll use our graphing calculators for that. So we'll check that out in just a second. But anyway, the initial number of kids infected with the flu, we're going to just take this t right here and we're going to make it a 3. So P of 0, not P of 3, P of 0. And we're going to have 100 over 1 plus e to the 3rd power minus 0. And when you go ahead and punch this into your calculator, and when you do that, the nearest whole number, when you punch all that in, is going to be 3. Oh, sorry, 5. My big beefy fingers. So when you punch this into your calculator, you're going to get 5. So here's A right here. There are 5 students infected on day 1. Okay. Day 2 then is derivative time. So we take our P of t, and watch this. I'm going to rewrite this guy. I want to make it 100 times 1 plus e to the 3 minus t power to the negative 1. That's the same thing as our original equation, but it's a heck of a lot easier to take the derivative of. And so when I do this, I'm going to have, dp dt, and that's going to be negative 1 times 100, okay, times, and then 1 plus e to the 3 minus t power to the negative 2, and then times the derivative on the inside. Okay? So when I take the derivative on the inside, that's going to be 0 plus e to the 3 minus t times, and then take the derivative of the 3 minus t part, which is negative 1. So that's a big derivative. That's a big derivative. But you've got to chain out the inside of this, and then you've got to chain out this guy. So that's where those things are coming from. So what's my derivative going to be? My rate of change of the flu with the population over time is 100 times e to the 3 minus t times 1 plus e to the 3 minus t negative 2. And if you want to, you can put the negative 2 guy on the bottom. But if we're going to punch it into our calculator, then it doesn't matter a whole heck of a lot where he's sitting. Okay, so to answer the last part of the question, what we want to do is check out part C. So when does the flu spread at its maximum rate? When does the flu spread at its maximum rate? Well, remember, when we're looking at our derivative, that is the rate of change. And so we're looking for then a maximum value of the derivative. Okay? And so what we're going to do then is go ahead and graph our equation of derivative and put that on your calculator. And when you do that, we'll find the maximum value of it. And when we find that maximum value, we will find the rate that we're growing. And so let's do that right now. So on your Inspire, we're going to choose to add a graph. And for f of x, we're going to go with 100 e to the 3 minus x power. And then parentheses, 1 plus e to the 3 minus x. And then close your parentheses, and all of that to the negative 2. So here's your graph, and wow, it goes way up there. So let's change that window. Whoops. And let's see. What if we go out to 30? Perfect. So here's our graph, and what we want to do is find the max value of that. So we're going to analyze this graph for a maximum, and we're going to tell it to start and stop. And so we get a maximum value of 325. Well, what does that mean? So over here, we've got our picture. So what we've learned then is that our flu bug is growing fastest at this point. Well, what does that mean? Well, the first coordinate is going to be the number of days that we're on, and the second coordinate is how fast. Okay. So to answer part C, we would say that when t is equal to 3, which is the third day, then the number of students affected would be 25 students per day. So then that P of t would be 25 students per day. And that's the fastest rate that it's growing. So a few steps, but not horrible. You can do it.